Chapter 15 has to do with running into transparent materials. Chapter 16 has to do with the concept of interference of light. It has to do with the wave, what happens when those waves, the light waves, interfere with one another. They're going to interfere just like all other waves via the concept we've already talked about in chapter 12, having to do with waves, the concept of superposition. The concept of superposition, that when the waves are in the same location, you simply add the value of the waves at that specific location, and you see what happens. And we have the two terms constructive and destructive interference. The easiest way to talk about this is actually to flip back to talk about sound a little bit. If you have constructive interference of sound, what do you hear? Jessica? Constructive interference of sound. That's okay. Constructive interference. We just have to review a little bit here so we can apply it to light. Constructive interference of sound. It's just going to be a little bit louder. Okay. What about total destructive interference of sound? Duval?
You don't hear it.
It's going to cancel out the sound. So that would be total and constructive and destructive interference of sound. So what do you think you see when you have constructive interference of light, Mitch? A brighter light, okay. What about destructive interference of light, Mitch? You're gonna have no light, okay. Now, the thing is, it doesn't quite work that way. In some ways it does, in some ways it doesn't. So we need to talk about the differences. So with sound, all wavelengths travel at the same speed. This is not true for light. And because of that, it doesn't quite work out that you get all bright light or no light. Now, this is an example of constructive and destructive interference of light. This particular effect is called thin film interference. It's actually not a part of this class. It has to do with the differences in thickness of the film of the bubble itself causes this particular effect. And what you see here is a reflection slash refraction of the light from the sky. Now, the sky, as I'm sure you're fully aware, does not actually have the full spectrum of the rainbow in it. So what happens here is you get constructive and destructive interference of light at different wavelengths, depending on the speed of that light, because the speed of the light is different at different wavelengths. And different wavelengths of visible light correspond to what, Sim? Different colors. So you can see this particular spot, we're getting constructive interference of the yellow wavelength. Here we're getting red. You can actually follow all the way through the Roy G. Biv if you want, because you have all of the various colors. Now, this is where you see the colors, where you see constructive interference of that particular wavelength of light. Now, this is true when we're talking about white light, which contains all the spectrums, all the wavelengths of visible light. It is slightly different when we talk about a specific wavelength, which we'll get to in a little bit. All right. So we need to review what it takes to have constructive and destructive interference. So going back, this is just a picture of constructive interference. Okay, so you can see constructive interference. These two waves are what are said to be, they are in phase with one another. And you can see that where we have a crest, and those two will add together, and we'll have a larger crest where we have a trough that will add together, we'll get a larger trough. So this is constructive interference. This then would be destructive interference. You can see where we have a crest, we have a trough, and those two waves are going to cancel one another out. So this would technically be total destructive interference. In order to have total destructive interference, there is a phase difference of how many wavelengths? What is the phase difference between these two waves? Wicked. It's okay. What we have to know the difference in the phase difference in terms of wavelengths in order to understand this. Mr. Chen.
Is it pi?
That would be in terms of radians, right? It would be 180 degrees pi radians. I agree with that. That's more math. I want to talk more in specifically having to do with wavelengths, in terms of wavelengths. Rick?
1.5.
1.5 would be an example. That's actually technically not what we see here. What we see here is a half a wavelength phase difference. But 1.5 would be another example. So we have you can have a half a wavelength phase difference. You could also have 1.5 wavelength phase difference would cause total destructive interference. What's another example of a phase difference that would cause total destructive interference? Kraus? 2.5, and we could keep going, right? 2.5, 3.5, 4,075.5 wavelengths. As long as the phase difference is off by an integer multiple of a half a wavelength, they will be out of phase. So notice, if we take and we phase shift this, such that we just shift it over by half a wavelength, they become in phase, right? These two then would be constructively interfering. Which brings us back to the first one. This is constructive interference. But notice what happens if we phase shift that by one full wave. We get constructive interference again. So what's another example of a phase difference that will cause constructive interference? Low.
2.
Keep going.
3, 4, 5.
Right. 2 waves, 3 wavelengths, so on and so forth. So it's this basic concept that we're going to use to build understanding of what we're talking about today. Because in order to get total and constructive interference and total destructive interference.
Hey class, do you hear me?
Yes.
Good. Hey class, do you see me?
No. So, when I am out in the hall and I yell, you can hear me, but you cannot see me. And this is because of the concept of diffraction. The sound is diffracted when it goes through the doorway. So, sound is a wave. You can see the sound wave going toward the doorway, and it is diffracted. What it means is it is actually sent out in all directions after it goes through this doorway. So, the sound, it comes through the doorway, and it's actually bent in all directions after it goes through the doorway. So technically, you could be standing right over there, this could be outside, and I could talk through this doorway, you would actually be able to hear me because the sound would actually be, because it's a wave, is bent all the way around and goes out in all directions after it goes through the doorway. Now, waves are only diffracted when they go through or around something that is close to the wavelength of that wave. So the reason this works for sound is because the sound waves from my voice are approximately close to the width of this doorway, and actually the height of the doorway as well. It does not work for light because visible light has a wavelength of approximately 400 to 700 nanometers, which I can't hold my finger distance from, right? It's a very, very tiny wavelength. So it's not diffracted as it goes through this doorway. But we're going to talk about and show examples of how light is diffracted when it goes through things that are on the order of close to the wavelength of the light. This is a good visual of water waves going through and around here, and we have the diffraction of these water waves as they go through here. So that is the basic concept of diffraction. The fact that waves will spread out after going through the waves bend and go out in all directions. Out. So waves will go out in all directions, will bend when going through an opening that is approximately the wavelength of the wave. Now, this is something that is difficult to see in nature, but this is a picture of this actually happening in nature. What we have is light going around, bending around the corner of a building. So it can work as well for corners. And what you see here is that the different wavelengths are bent at different angles, and therefore they're running into this cloud, and you can see that the wavelengths are bent at different angles. So you have constructive interference and destructive interference at different wavelengths, hence different colors. So this is not something you normally see because light has to be both bent around the building and then has to run into something, a cloud for example here, so that you can see the effect. Okay, so now we need some more definitions. Coherence. Coherence is when you have two light sources in phase with one another. We're going to have to use coherent light in just a minute, so I have to define that. We also are going to talk about monochromatic light. Monochromatic meaning, Curry? We've already talked about polychromatic. This is monochromatic.
There's one of something.
One of something, yes.
One of a wave.
One wavelength. Or you could also look at it as one, because we're talking about visible light, one wavelength of visible light will be one. It's got a form. One color, right? Because that refers to color. One color of light, one wavelength, monochromatic light.